Hi all, my name is Tudor Popescu and I am a PhD student in the mathematics department. Today I would like to talk to you about the William Lowell Putnam Math Competition, which is the most important math competition in the world for undergraduate students. Um, Only students from colleges in the US and Canada, and more recently in Mexico, are allowed to compete in this competition. Um, Other than this, I would also like to talk a bit about the Brandeis preparation program for the Putnam. As I was telling you about, the Putnam is the most important math competition in the world for undergrads, and it's also one of the hardest or infamously hard math Olympiad math competition. That is because the median is either 0 or 1 points. And even though there are 12 problems in the competition, each worth 10 points. So the maximum score is 120. No one really gets 120. I don't even know when the last time this ever happened. Getting even 1 point is an impressive achievement on its own. Getting solving one problem that is getting 10 points is already something that's really good and something that you could put on a resume. Um, and usually getting around 25 points would place you among the best 500 scorers in the country, which automatically gives you an amazing boost for finance companies, for example. As I said, just making top 500 in the Putnam is something that you could definitely put on a resume and boost you for if you're applying to industry jobs. On the other hand, if you're applying for PhDs or master's program, similarly, getting a good result in the Putnam would definitely give you a leg up in applications. So this is one reason to compete in the Putnam. I definitely did that myself when I was an undergrad. Um, and then this, some dates. So the competition always takes place in the first weekend of December, namely the first Saturday of December. Um, and about Brandeis, so Professor Kiyoshi Igusa and I offer weekly practices twice a week in Goldsmith. Um, and we do have some very different approaches to it, and I think we complement each other really well. So Professor Gusa presents some problems from previous exams, whereas I lecture a bit about different topics that could be on the exam. So I think the way we organize this is really, really good in the sense that you also learn some different techniques and you also see some problems that appeared in the previous years and get some hands-on experience with solving some Putnam competition problems. All right. Um, Without further ado, so I already explained a few reasons why you should compete in the Putnam from, I guess, an individual point. Again, you could definitely boost your resume. And also, I think if you love math, then it's a great experience just to learn more math and kind of bang your head against the wall against some really hard problems. Last but not least, if you do well on the Putnam, you definitely get some bragging rights. So if you do better than your friends, you could definitely brag about it on TV shows. So without further ado, let me just share a video in which Steve Ballmer brags about beating Bill Gates. Let me start sharing. Okay. Um, so I will shut up while still Steve Ballmer talks.
Is it true that you once beat Bill Gates? Because you guys went to college together. You beat him in a math competition?
I did.
This is fantastic.
I did.
And I hope this stirs up animosity between the two of you. Let's go. What was the competition?
The Putnam Math Prize competition, well known to most people in the world, I'm sure.
Yeah, we've all been through it.
Yeah.
And so what happened? And Bill he was younger than you, and you guys were in the same competition. Is that right?
Same age. Same age.
Oh, you're
yeah.
the same age.
I'm 6 months younger.
Okay.
5 months.
Yeah. You're in the
uh,
same math competition, and I would think Bill Gates would be an incredible math whiz.
He was a math whiz. He finished 10th in our dormitory at college.
Uh-huh.
10th in our dorm.
And what about you?
I was about second in the dorm, 57th in the country, but who was counting?
Yeah. Steve, before you announced your math stat to me, did you really go?
I can't do it again. I'm speechless.
That's the craziest. And you know what? I was first in the math competition.
All right. So, yeah, as you can already tell, a lot of, very important tech people and CEOs have competed in the Putnam. More importantly, for mathematicians, oops, that was the Conan video. Yeah, more importantly, for mathematicians, a lot of very famous mathematicians have competed in the Putnam and have won it and done really well. Uh, Also, a lot of famous physicists have competed in it, such as Richard Feynman, who famously developed the Feynman integration trick, I think when he was preparing for it. So, yeah, so as I was saying, I think you should really, I think it's a great idea to compete in the math, in the Putnam competition. A bit about the Brandeis practices. So, as I said before, Professor Igusa and I organize by weekly meetings, and I guess bi-weekly. Yeah, so we meet twice a week in Goldsmith. What I hadn't said before is that we receive free pizza from the math department while we prepare. So you could have pizza during the evening, which is pretty great. Other than this, we also, if you take the competition on the first Saturday of December, we go for lunch at some local restaurant. We try to change it up every year or every other year, but it's usually some really good food. Yeah, so if you'd like to spend 6 hours doing math in December, then yeah, at least you get some nice free food. The structure of it is that there are two different events. So the first 3 hours what is comprises the session A of the Putnam. So that happens between 10 a.m. and 1 p.m. on the Saturday, and then between 4 and 7 or 3 and 6, if I remember correctly. That is session B. Again, 3 hours, and you have 6 problems per session, which totals to 12 problems per competition. Okay. Other than this, so you would also get more bragging rights locally, not necessarily on TV, because if you do well, let me start sharing again. So if you do well, the Brandeis website as well as the Justice will interview you. So yeah, you can see here. Um, yeah, so in 2023, we ranked 37th. I forgot the exact ranking for the other years, but in the last few years, we usually rank between 30th and 50th. So Brandeis does pretty well in the competition. To brag to not to brag myself, but also as I said, I think we have a pretty good training program. Um, so I think the students learn a lot. So if you choose to go for the training program, you would also learn a lot and also receive some nice pizza. Um, yeah, so let me stop sharing. Again, the training is pretty comprehensive, and I think you would learn a lot of topics taught in undergrad math in a fairly relaxed way without the pressure of any grades and amongst your friends and peers. And yeah, and also free pizza. So, yeah, without further ado, let me talk a bit about the Putnam competition this year, about the problems. Um, so let me start sharing again. Okay, so these are the problems from the 86 William Noel Putnam Math Competition. Again, this happened on Saturday, December 6th. All right, so I think the first couple problems, I would say they're kind of coupled together. So A1 says the following: if m0 and n0 are distinct positive integers, and for every positive integer k, define mk and nk to be relatively prime positive integers such that mk divided by nk is 2mk minus 1 plus 1 divided by 2nk minus 1 plus 1. And the question asks you to prove that 2mk plus 1 and 2nk plus 1 are relatively prime for all but finally many positive integers k. In my opinion, this is a very hard problem for the first problem on the Putnam. That being said, the second one, namely A2, is a bit on the easier side for for the second problem on the Putnam. Um, the difficulty of A2, in my opinion, pretty much comes from just doing some calculus. That's not necessarily nice, but I think it's kind of forward what you'd have to do to get the constants if you have some Putnam practice. All right, so A2 says the following: find the largest real number A and the smallest real number B such that A times X times pi minus X is less than or equal than sine of X, which in turn is less than or equal than BX times pi minus X for all X in the interval 0 and pi. So I do think these are kind of nice problems to think about and kind of bang your head against the wall a bit. So let's move on to some other problems. And at the end of this video, I will also solve one problem, but I haven't talked about that one yet. All right, A3 I think is very beautiful. It's pretty hard. Um, oops. Yeah. So Alice and Bob play a game with a string of n digits, each of which is restricted to be 0, 1, or 2. Initially, all digits are 0. A legal move is to add or subtract 1 from one digit to create a new string that has not appeared before. A player with no legal move loses, and the other player wins. Alice goes first, and the players alternate moves. For each n greater equal than 1, determine which player has a strategy that guarantees winning. This is a very beautiful problem and very hard as well. Um, Spoiler alert, Bob always wins if n is bigger than 2. So, yeah. I think, again, I really like this problem because it's very easy to understand, right? But then it's really hard to prove. So I think in a lot of Putnam problems and in math in general, it's very good to start working on smaller cases first. So this problem is really one of these problems where you have to look at small cases first, kind of see what Bob can do to always win, what he can do to force Alice into a losing position per se, um, and try to generalize this for larger n. Okay. A4 is the following. It's A4 is already starting to get hard. It's still nice and very easy to understand. Um, and also you do need some linear algebra. So A4 says the following: find the minimal value of K such that there exists K by K real matrices A1 for A2025 with the probability that AI AJ is equal to AJ AI if and only if the absolute value of I minus J is 0, 1, or 2024. You do not need to know linear algebra to compute in the Putnam, but usually there's one problem mode of the 12 that is linear algebra. So one or two. Yeah. A5 says the following: let n be an integer with n greater or equal than 2. For a sequence S1 through Sn minus 1, where each Si is plus or minus 1, let f of s be the number of permutations a1 through an of 1 through n, such that Si times ai plus 1 minus ai is bigger than 0 for all I. For each n, determine the sequence. The sequence is S for each f of s is maximal. Again, this is already starting to be really hard. So I do not want to talk about this problem because I would spend a lot of time. A6, again, in my opinion, this is probably one of the most beautiful problems of this year, but also one of the hardest. Let b0 be 0, and for n greater or equal than 0, define bn plus 1 be equal to 2bn squared plus bn plus 1. For each k greater or equal than 1, show that b of 2k 2 to the k plus 1 minus 2b to the b of 2k 2 to the k is divisible by 2 to the 2k plus 2, but not by 2 to the 2k plus 3. As a number theorist myself, I really like this problem. Okay, so usually I hadn't mentioned this before, but usually the problems go in order of difficulty. So A1 is a bit easier than A2, which is in turn is a bit easier than A3, and so on and so forth. So A6 is the hardest, usually is the hardest problem of the A part. And then B1 is around the same level as A1, B2 is around the same level as A2, and so on and so forth. B1, this is actually the problem that I will talk about. So suppose that each point in the plane is colored either red or green, subject to the following condition. For every non-collinear points ABC of the same color, the center of the circle passing through ABC is also this color. Prove that all points of the plane are the same color. as I said before, I will talk more about this problem at the end of this video, so stay tuned. All right, V2. Um, I don't really like this problem. It's pretty bashy analysis. In my opinion, it's just, again, it's not really hard. It's just complicating something that you can do. I guess, yeah. So I won't really talk about B2. So let f be function from 0, 1, 0, 1 to 0 infinity. That's strictly increasing and continuous. Let's say that R is the region bounded by x is equal to 0, x is equal to 1, y is equal to 0, and y is equal to f of x. Let's say that x1 is the x-coordinate of the centroid of R, x2 is the x-coordinate of the centroid of the solid generated by rotating R around the x-axis. Prove that x1 is less than x2. Okay, B3 is a problem that I really enjoyed. Again, I'm a number theorist, and yeah, during the competition, I was working on this one and solved it. I think it's a fairly, if you do have experience with math competitions, I think it's kind of straightforward what you have to do. So again, that's why you should come to the Brandeis Putnam practice because we talk about problems like this very frequently, and it would definitely give you a leg up in solving problems like this. So B3 says the following: suppose that S is a non-empty set of positive integers with the property that if n is in S, then every positive divisor of 2025 to the n minus 15 to the n is in S. Must S contain all positive integers? So the answer is as spoiler alert. Okay. B4 says the following. This is a second linear algebra problem. Let's say that A is an n by n matrix of non-negative integers such that aij is 0 when I plus j is less than or equal than n. AI plus 1 j is either aij or aij plus 1 when I is between 1 and n minus 1 and j is between 1 and n. And aij plus 1 is between aij and aij plus 1 when I is between 1 and n and j is between 1 and n minus 1. Let's say that S is the sum of the entries of A and let n be the number of non-zero entries of A. Prove that S is less than or equal than n plus 2 times big N divided by 3. Okay. Yeah, pretty nice problem. Again, it's already pretty hard, so I will not really talk about this one. Okay, B5, again, as a number theorist, I thought this was the most beautiful problem on the competition, but it's also really hard. So B5 is really hard. Let's say that P is a prime greater than 3. For each K in 1 through P minus 1, let IK be the modular inverse modulo P. So that is IK is a number between 1 and P minus 1 such that K times I times K is congruent to 1 modulo P. This just means that K times I times K gives residue 1 when you're divided by P. Prove that the number of integers K between 1 and P minus 2 such that IK plus 1 is less than IK is greater than P over 4 minus 1. There's a couple of solutions, of official solutions to this problem that are very nice. So again, it's already a hard problem. So if you do have time over break, you should definitely think about it. Okay, B6, I also really enjoyed. I think this is the most research-oriented problem of the Putnam, and it's something you'd kind of encounter in research. So let's say that n is a set of natural numbers. Find the largest real constant r, such that there exists a function g from n to n, such that g of n plus 1 minus g of n is greater or equal than g of n, everything raised to the r, for all n in n. Again, for this, you should definitely play around a bit. Just think of like what r should be. So, and what, if you have a nice function g, what would r be in that case? Okay, great. So these were the problems from this year. Let me talk a bit about B1. So let me stop sharing and start sharing B1. Okay. Unfortunately, my stylus pen doesn't work, so we'll see how I how I do this. So again, B1 is the following. Suppose that each point in the plane is colored either red or green, subject to the following condition. For every 3 non-collinear points ABC of the same color, the center of the circle passing through ABC is also this color. Prove that all points of this plane are the same color. All right. So without loss of generality, so this is something that mathematicians do a lot. So we can assume for the sake of contradiction that there are 2 points that are colored in a different way. So let's say, I don't know, let's say this one is green, say, or it's probably better to do it lower because I will draw a lot of circles. So let's say A is green, and we also have a red point, B. Okay, that's a point. Let me draw the green a bit so you can see it better. Okay, one green point, one red point. All right. I apologize in advance for the ugly handwriting as well as probably the ugly circles that I will draw. Okay. Um, so with this in mind, okay, this problem really reminds me of Sudoku because you kind of have to, if you were a sort of Sudoku, like you have to look in some like lines and columns, rows and columns, or like the square to be like what to kind of see what numbers you can put, or particularly what numbers you can't put. And usually you're just gonna have like, oh, there's only one number that can be put in this place. Um, and similarly, in this problem, we're gonna look at different points and be like, this cannot be red, so it must be green, or the other way around. And at the end of this problem, we'll see, oh, this point cannot be green, but also it cannot be red, so it's impossible. All right, so again, assume for the sake of contradiction, we have two points of distinct colors, A and B. So now let's draw a circle through A of radius AB. As I said, I apologize for the bad circle drawings. Okay, and similarly, we're gonna draw a circle through with center B with radius AB as well. Okay, the important part here is that we have 2 points at the intersection of these circles. Okay, let's say these are C and D. Okay, we're not gonna name them yet because, well, if C and D are, actually, let's name them because we don't know yet what color they are. But if C and D are both green, well then A, C, and D are green points on a circle with center B. And this cannot happen because um, again, if we have 3 points of the same color, then the center of the circle passing through them has to be the same color. So B would have to be green. Okay, so obviously this cannot happen. And similarly, if C and D are red, then B, C, and D are 3 red points, and the center of the circle passing through them is green. So again, this is impossible. All right, so it means one of them is green and the other one is red. We can say this one, like without loss of generality, we can say that C is green and D is red. Okay, so far so good. Feel free to pause the video if there's any, um, if there's anything that's not clear. All right, now let's draw more circles, shall we? Um, so similar to what we did before, well, it could be useful to draw circles through, for example, D, right? D and C, well, since these are the new points. So let me draw. Okay, so also note that actually before we begin drawing the circles, these are all the same length. Let's say this length R, the radius of the circle. Okay, so namely AB is equal to AC equal to BC equal to AD equal to BD. All right, so now let's draw a circle with center D of radius R. So this passes through AB. Okay, cool. And also we can also draw a circle through with center C through AB as well. So again, this will have radius R. Okay. Again, horrible handwriting. Sorry about this. All right. Well, let's see what happens here. So, okay, this is also of length R. Let's say this is E. Again, this is also of length R, even though it doesn't really look on my drawing. All right, let's say this is G, and let's say this is H. Okay, so what can E be? All right, so let's look at this point. What color is it of? Um, All right. Well, if it were red, so let me, okay. If E were red, well then, actually I should probably, let's draw this as well. Okay. All right. Well, first of all, note that um, this is on the intersection of two circles. So also we know that AE is of length R. Okay. So in particular, well, B, D, and E are on a circle centered at A. So if E was red, then A would have to be red as well, but A is green. So this is not the case. Therefore, E must be green. Okay? Now, similarly, let's look at G. Well, if G, namely this guy, okay, if G was red, then similarly G, B, and D would be red points on a circle centered at A, which is green. So obviously this is impossible. Sorry, this was G, right? So G has to be green as well. Okay, so far so good. Let's look at F now. Okay, namely this guy. Okay, well, if F was green, then A, E, and F would be green points centered at D. Okay, but this is again impossible because D is red. So it means that, let me draw it with red, that F must be a red point. Okay, last but not least, let me draw it in black. So age, also these are of length R. Again, circles. My drawing is pretty bad, but yes. Um, okay, length R. All right, let's look at age. Well, if age was, I don't actually think we need age, do we? But let's do it for the fun. So what do you think age should be? You can pause the video. Um, okay? Yeah. So also, if we argue in the same way, well, if age was green, then A, C, and age would be green points on a circle centered at the red points. So obviously that's impossible. So this means that G has to be red. All right. We kind of okay, we're kind of done. We already have a contradiction. Okay, let me find it. All right. Where is the contradiction? Let me see if I remember it. Okay. So this was, oh, oh yeah, we do need another one, right? Oh yeah. Okay. All right. Oh, yes. Exactly. All right. Okay. So, all right. Last thing. So let's look at the rhombi. So A, B, C, G. Oops. A, B, C, G. And A, B, D, F. Okay. Let me draw this as well. These are kind of, they're congruent to one another, right? They have, well, they're kind of formed of two equilateral triangles with side length r. Okay? So in particular, we have that AF is equal to AC. All right. Now, through A, let's draw, so namely, we can draw the circle so draw the circle centered at A with radius AF. Okay? Now, this circle, so let me erase some of the circles we don't really need, just to have I guess, yeah, have the drawing look a bit better. Okay, so we only kind of need one circle at this point. And we draw, again, the circle centered at A with radius AF. So this will pass through F, and this will pass through G as well. Okay, and whatever, it will intersect the circle centered at D with radius R. Let's say it intersects at some other point here, let's say X. Okay, the real question is, what is the color of X? Okay, so first of all, well, X is on the circle centered at D with radius R. So X should be red, because if it was green, then E, A, and X would be green points centered on a circle with center red. So that's impossible. Okay, so we must have that X is red. Okay. On the other hand, if X is red, then X, F, and G are red points centered at a circle with, on a circle with center A, which is green. So this is impossible. So from here we get that X is green. Okay, but this is not Oppenheimer. You cannot have something that's both green and red. So here we get a contradiction. So this is a contradiction. X cannot be both red and green at the same time. Okay, so therefore, again, we started by assuming that there exist two points of different colors. So we got a contradiction. So therefore, all points in the plane have to be the same color. Okay. I hope you enjoyed this problem, and I hope you enjoyed learning a bit about the Putnam competition. So yeah, hopefully you will join the Putnam preparation program next year, and I'm looking forward to seeing all of you. Okay. Yeah, have a nice semester.